Hi, I'm Kevin. My project is distributed testing for robust inference under the guidance of Dr. Nick Gasolfi, Dr. Carl Miller, and Professor Artur Dabrowski in the Auton Lab as part of the Robotics Institute Summer Scholars Program. So, what's the problem? We know that robots are often specialized for specific tasks in certain environments, so they might have different sensor packages for different conditions. However, communication between these robots can often be expensive and unreliable, especially in terms of battery life and other considerations in the field. So, even though it might be useful to consult with these agents at certain points, it can often be infeasible or we might have issues in doing so. As a result, we look to explore a new framework for leveraging expert agents with individual data in a communication-limited environment. When we look at the system design, we can see that there are two agents, which we can imagine are robots, and an oracle, which is some centralized server. So in our training procedure, the oracle can send training data to both agents, where the agents are able to send their predictions back to the oracle using their locally trained classifiers. Then the oracle will use those return values to train an assignment model, another classifier. This classifier will be able to determine which agent is best suited to predict on new data points, which is what we see in the testing procedure, where an oracle will predict the best agent, and then the agent will return its prediction to the oracle, which will then send it back to the user. Now, when we look at the data, we're using the Fashion MNIST dataset, which has 70,000 data points and is a classification task with 10 labels. Here, the oracle and the two agents each have 1/3 of the data, while the two agents have a fairly standard 80-20 split between the training and the testing data, with some number of shared classes and some number of private classes. The oracle has a very small percentage of training data, which is how we simulate a low communication environment. Then the oracle that has access to all of the classes is able to assign points with their test data to better understand the performance, even with a very small amount of training data. What we see in terms of performance are that the random forest agents outperform the k-nearest neighbor agents generally, but that the mix of one random forest and one k-nearest neighbor agent appears to perform more similarly to the two random forest agents. This is quite interesting because it suggests that the random forest agent is almost able to improve the performance of the k-nearest neighbor agent, where the oracle understands that one agent might be better than the other. Also, we have a perfect allocation baseline, which is where the oracle will always assign correctly, and an adversarial allocation baseline, where the oracle will always assign incorrectly. And as expected, our experimental results fall in between these two. We can simulate concept drift with randomized labels. So what we see in the graph here is the blue line is what we saw previously on the last slide, and then the yellow line is where labels become increasingly randomized in the data set for one agent. So as you can see, the performance is much worse. But when we retrain the oracle to be aware of this fact, we notice that the performance seems to approach that of the no corruption scenario as the number of shared classes increases. This makes sense as the oracle becomes much more reliant on the non-corrupted agent to make accurate predictions. Now we can look at how the oracle assigns points between these two agents. With each agent receiving half of the training data for each shared class, you might expect that the test split might look similar. However, what we see is that agents seem to develop specialties where even in classes where they both have the same amount of training data, the oracle seems to vastly prefer one over the other. For example, on the left here, we see agent A is much preferred for class 4, versus on the right here, agent B is much preferred for class 4. What we see is that this system is able to demonstrate the potential for a distributed classification network, satisfying the conditions that it is able to incorporate knowledge from expert agents, respect agent data silos, and minimize overall communication in the network. However, there is still much to be explored, with future work looking at exploring concept drift in terms of system accuracy over time, and moving beyond two agents, where less effective agents may help recover from corruption of expert agents. Also, we are interested in looking at new datasets and models to explore greater contrast in model quality. Thank you very much.